Thanks, and welcome everybody to our talk, Digital Twin at Schaeffler. So usually when you think about digital twins, you will think about maybe analytics, maybe simulation. However, we actually brought a slightly different topic today, simulation combined with IoT, as well as smart service discovery. And in the course of this talk, we will showcase how this actually brings value to Schaeffler, how you could maybe do something similar at your company and your enterprise, and what actually we learned at Schaeffler that could help you. So let's start with that. So first of all, I guess everybody knows Schaeffler as a big automotive and industrial technology leader. However, just a couple of key facts. So we are actually, of course, a global enterprise with a vast variety of different products, currently driving the e-mobility, the autonomous driving, and at the same time, as we'll also showcase later, innovation in the wind, in the railway sector, so across various sectors, so not just automotive. So maybe to also look at the topic of digital twin here in a nutshell. So what is Schaeffler doing with the digital twin, and how are we doing well, novel digital services by means of this piece of technology? So first, of course, we must ask ourselves, okay, why is the digital twin actually important? What is the digital twin at the end of the day? It's a huge buzzword. Everybody has heard it a couple of times, read about it, and so forth. But what is it at the end of the day? So essentially for us, it's a digital representation of a physical thing. So you may have a physical product, you may have a machine at your shop floor, you may have some other physical asset that you want to monitor, that you want to control. And for that to happen in a digital way, you need some representation of it, yeah. And that's in essence the digital twin, yeah. It is data, it is functionality about a physical thing. We focus much on the product side, so we focus on our mechatronical products, but also on our mechanical products, and try to represent them in a digital way so that they're optimized during production, during engineering, as well as enhance them by means of new digital services that then again drive value to the customer, basically. So that's our goal here. So that's, of course, a very, let's say, broad vision and a very high-level vision. So how could we achieve that? So what is our, let's say, strategy behind that? Our strategy is basically a platform as a service approach, if you will. So we are building a framework, a platform on our cloud infrastructure that is able to accumulate or to integrate various different data sources of our products, from the engineering, from the production, as well as from the field, as well as the services. So basically the functionality. So of course the product has some functionality in terms of its sensors and actuators, but also maybe there is some, let's say, product functionality in terms of systems. So systems may have also functions. And we basically gather these different functionalities and these different data pieces in our cloud, in our digital twin framework, where we have different components. We have things for ingesting the data. We have things for storing and integration in terms of a knowledge graph approach. We have things, and we will talk about this in a bit more detail, of our, let's say, product simulations here, about analytics and AI services that are interlinked also. And then, of course, we want to expose all of that later on to the customer, to our partners, by means of services, by means of APIs at the end of the day, which also, of course, need to be discovered, need to be found, if you will. So seeing that framework, seeing that vision, still we need to make it more concrete. What are the very, very precise values, business values that we are creating with that approach? So we do have a different, let's say, use cases in our portfolio. We do have different projects that we're working together with units, business units here at Schaeffler. So starting at the left-hand side, we are doing a twin project with our automotive colleagues, providing, let's say, an approach to really, let's say, forecast the quality along the supply chain of our products. So not only taking our quality measurements, our end-of-line measurements, but also taking into account quality measurements coming from actually the next, let's say, partner in our value chain, which gives us feedback, gives us, let's say, information also from their testing facilities, so that we can basically learn and train our quality measurements to be very more accurate and also in a, let's say, larger system context. For this, of course, we need AI, we need the API interfaces and so forth in order to really integrate these two different partners. On the other hand, we also have a very large project with our industry colleagues in the wind department, where we basically have a novel approach to really showcase how a main bearing in a wind turbine can be sensorized and can be equipped with novel sensors in order to produce additional KPIs, additional statistics about its usage and about the loads on this wind turbine. And lastly, we have a very interesting project with our industry rail colleagues, where we can really use, let's say, engineering and also production information during the maintenance process later on, when the, let's say, customer returns the products to us and we maintain it, we repair it in order to, let's say, improve this process and in order to make this process of maintenance and more efficient at this point. So this is just maybe a small glimpse of different projects that we have been working on in the past and are currently working on, in order to show you concrete business values where a digital twin and such a framework that we are building comes into play. So now, as promised, maybe a little bit of a different angle to look at the digital twin, so that you also maybe can take some new ideas maybe and use them in your setup. So from us, this is a big lessons learned. We really must make really sense of data. So then data is always nice. You always can get lots of data. So you have IoT data, you have data in your enterprise systems, but really data is meaningless without context. So metadata is really key in order to make use of it, in order to integrate it, in order to, and especially in a digital twin context, when you have IoT data, you really need to annotate it with metadata in order to use it later on in your simulation as well as your analytics service. And this is what this picture a little bit shows here. So on the left-hand side, we have, of course, the ingesting of this data. We have the annotation of this data here in the center, a distributed query engine that can query and integrate this data. And then basically we have the users of this information together with the meta information here, these services, and the consumers on the right-hand side again. So, but again, the key point is that making sense is really essential here. Also, what is sometimes a little bit forgotten is really finding the right models. So in terms of simulation, also in terms of analytics, finding out what models could be applicable here and on what models have been also created in the past that may be applied. So also models, so simulation as well as analytics models have or should have metadata, should have data describing how these or what these simulation, what these analytics services are actually doing for what kind of products they are relevant, for what kind of services they could be used, what kind of outputs they produce, and so forth, in order to have kind of a discovery later on to foster reuse. Yeah, because when you have a simulation service, when you have an analytics service, you may do it once for a particular product or a particular, let's say, instance of a product, but it may be also applicable to a variant of this product. It may be applicable to another, let's say, similar product, and so forth. And you may also want to integrate it later on with other, let's say, services. So therefore, metadata and discovery on top of that is very essential. And lastly, and here I also want to give the word to my colleague, Andrei Dektiarev, who will then also show a short demonstration how this looks in a tooling. We also think gray box is a huge topic. So really combining simulation and analytics in order to foster, let's say, the insights here. So simulation on the one hand side, a very well-known, of course, thing that has been done for many years, mostly during the engineering phase of a product. We are creating simulations in order to design the product according to specification. Yeah, but this knowledge is not only valuable during engineering; it also can be used during later on phases, during in-use phases of the product, where we actually also want to have information about how a particular product behaves, what kind of loads it could endure, and so forth. So this kind of domain know-how we must use also in later phases. However, at the same time, we also want to use data as a, of course, knowledge driver, yeah, in order to forecast the product behavior based on data, based on algorithms on that data. And putting these two together may actually be a very good approach when you have incomplete information about a domain, may be a very good approach when you have existing domain know-how, but it's not also not quite complete. So combining these, in our experience, is really a huge benefit, also in terms of stakeholders. Meaning we have here the typical engineer that can construct the simulation service, can bring in his domain know-how, and at the same time we can work together with a, let's say, development expert here on these algorithms, a data scientist, machine learning engineer, and so forth, who then maybe can add additional, let's say, know-how here. And how this looks like, maybe Andrei, you can jump in and showcase a little bit of this approach.
Okay, thank you, Andreas. Do you hear me?
Yes.
Perfect. Good afternoon, ladies and gentlemen. Now I'm going, let's say, to show you the more practical parts without any PowerPoints, a small demo session. How we're working, how we deal with the Schaeffler know-how, Schaeffler domain knowledge. A couple of words about myself. I'm by Schaeffler, I'm already 20 years. My money with mechanical engineering, I earn in 2 years, 30 years. And although my first touch to the neural networks was in the 90s, I still remember the time how the traditional mechanical engineering world is working, and I also observed what's the huge challenge to bring this is new modern technology, clouds, machine learning together with the traditional or existing knowledge. So I'm going to share my screen. So I think, Andreas, you should unshare your screen before I. Okay.
Yes.
So let's do it. Okay. I hope you see my screen. On the screen, you see I think the most famous product from the Schaeffler. It's the rolling bearing, and the rolling bearing here. It's again, it's one of the main products. And if you know Schaeffler even more close as the just rolling bearing manufacturer, you know that's the rolling bearings. They're not the cheapest ones which you can buy in the world, but it's a very good reason why let's say we have sometimes higher prices for our products. Of course, one of the reasons is the good quality of our products. And there is another reason. One of them, we also provide to our customers calculation service where we can say, okay, this bearing is fit for your needs and fit for your application. Important is that we are not only consider rolling bearings as standalone. Here is, by the way, our software bearings, which we use for, let's say, calculation service for our customers since many, many years. And in this software, together with the customers, we not simulate, calculate only rolling bearings standalone, but we can simulate the complete drivetrains. You see here, it's a drivetrain from wind turbine application. It can be spindle system. It can be any other mechanical system. And important, this is bearings, our software. It's also used by our customers directly in their companies. So if you create such models, simulation models, there's usually joint work between chef engineers and the engineers from our customers. What's actually these models are able to do? Here you see on this part, usually, not usually, it's always attached the blades, wind turbine blades, rotor from the wind turbine. And if we, let's say, okay, from the blades, we receive the load from the wind. With the help of simulation model, we can calculate the loads in the rolling bearing. We can calculate lifetime of rolling bearing, not only from this one, but from another rolling bearing. So we can calculate how the gears are working. We can calculate friction inside of the system and many, many, many other parameters, which is, let's say, possible and very important to understanding how it's working the system. So in the case of this desktop simulation, we just put some imaginary loads, virtual loads here, but the idea is really near. It's just to put here, for example, loads which we measure on the real wind turbine and calculate in parallel to the, let's say, operation of the wind turbine. This is KPIs like remaining use lifetime, friction again, whether any damages modes we can let's expect from the system. That's what a general idea, let's say, very straightforward idea to the digital twin. The problem is that this application is the desktop application, and this application we need to bring somehow in cloud. And for, let's say, for this step, we use another application, our also application which we developed in simply internally, where we just described what kind of input loads we have for the bearings model, what kind of results we receive from this bearings model, because bearings usually produce hundreds of different output results. Here, for example, we request only let's say 2 of them. So this is, let's say, description is done locally on desktop, is done by application engineer. And what's the last step need to be done in order to use this is, let's say, models in the context of digital twin. We just need to take this is 2 files, this, let's say, description, what we're going to do with bearings model and the bearings model itself. And we just need to upload into the clouds. And if the clouds, we have this, let's say, configuration, the calculation services running automatically, and so we, let's say, have, let's say, digital representation, digital twin of our real application. Why we bother about this approach? Such models usually it's a really concentrated, huge amount of knowledge of domain know-how from our application engineers, and these models are prepared by application engineers, and actually there is no any big needs, let's say, to explain our IT experts what is actually stays behind. This is challenge of our application. This is, let's say, the meaning of application, the point of application is modeled by our application engineers, and IT experts just to deploy this model in the clouds, and everything is working. So we save a lot of loops in the let's say discussion between engineers in different domains. We save misunderstanding and so on. And this is a kind of white box models, what Andreas told before. This is the model which we are, let's say, can analyze, can see everything. This is model can work in the clouds as well, or even on the edge if the edges have enough processor power. But if it's thinking about the system which doesn't have enough computer power, or it is a limitation from the operation system and so on, there is a possibility, let's say, to develop so-called gray box models. It's a kind of substitution model based on machine learning algorithms, which can be derived from this is a simulation model and how it's work. It's working a little bit different. It's again, we generate small workflow with few steps. The first step in such workflow, it's a design of experiment where we generate a lot of inputs. Here, for example, with Lightning Hypercube sampling method, put this as inputs in our simulation model. This is inputs. It can be 100,000 or even more combination in loads or whatever. This is a combination are calculated in clouds. That's also why we use clouds in this case, because it's of the huge amount of calculation. We get also automatic scaling of computer power in the clouds. Here we see Azure service, which dependently how many computer power we need. It's initiate additional instances, calculation since and put them back if we don't need them. And we pay only for how much we use, so much we pay. Okay, and after this is calculation in clouds are finished, we train a machine learning model. Here we use different algorithms. We have a pretty good experience with gradient boosting algorithm, XGBoost. And if the model is trained based on data generated by simulation model, we receive in this case a so-called gray box model, and they can use this as gray box model again in clouds as a substitution for our simulation model. We can use this gray box model on the edge, or we can even put this gray box model into the sensor and receive such smart sensor, which is probably very small with very low power, but it's able to calculate, to predict, for example, friction in the rolling bearing or similar KPIs. Also important that such workflows are created again, not by a data engineer, but again by application engineer who knows about application, who knows the meaning of all the data which we have here. And in this case, data engineers just need to support our application engineers to point him some, let's say, which kind of hyperparameter we need to use for the machine learning, and the rest is working more or less automatically. So this is, there was one further small point, which probably is not looks very spectacular, but it's also helped a lot to get our application engineer involved in development of the new solution. It's such services like BI services, and in this case, Power BI services. Such, let's say, simple dashboards are created by application engineers with the focus of their needs. Here we see the live data from one phrase machine with another smart sensor. And again, the application engineer, if they're able not only, let's say, consume the data, but also present data in the form which is most suitable for him, for his needs, we save again a lot of time, a lot of efforts, a lot of misunderstanding. Okay, that was my small demo part. I give word before I give word back to Andreas. Takeaways on the Scheffler, we make a lot of thoughts how we involved our application engineer in creation of new digital services, how we simplify, let's say, creation of the new digital services, and also demonstrate that we have tools where we can each time and very fast decide whether we need a white box model, gray box model, or whatever. Okay, thank you, Andreas. I think I need unshare.
Thanks, Andre. Thanks, Andre. So I think we're also at the end of our time. So maybe we can just open up for questions here and then give the audience a chance to ask some.
Thank you to you both from our side here in Berlin. So to the audience, do you have any questions? Okay, it's afternoon, right? I have one question. I have made the experience that VW is at the moment forcing, in any case, to drive digitalization, okay? So they started the project DPP, Digital Production Platform, and I think it has a relation to the engineering inside VW in future too. So if you put your data from your parts, perhaps you deliver later to VW, right? Into Greengrass, into Microsoft Azure, and VW puts the data from her own systems into Amazon Greengrass. So in future, my question is how it could match together.
Yeah, that's a very good question. So I think we explained this a little bit in the use case from the automotive colleagues also, where we share quality data and also try to predict quality in a different manner. So in a way, digital twin for us is really also an enabler along the value chain to ease engineering, to ease also production quality issues. So I think this data sharing and also collaborative engineering along this, let's say, value chain is essential. Yeah. So of course, there will be many different, let's say, cloud providers, many different, let's say, technologies that would foster such a or enable such a data sharing. I think technology is not such a big deal. I think the meaning, the semantics of the data and getting, let's say, the right, let's say, things together again is the key problem. And for this is also, let's say, what initiatives like Platform 4.0 or other, let's say, similar initiatives are targeting. So really semantic models for the data in order to foster the integration. Yeah.
Okay, thank you so much. Okay, to you both, thanks from our side here in Berlin, from the audience. Thank you.